problem? All your yeah, starting to record. All your family, etc., are all fine. Anybody has a problem? Okay, good. Hitesh is answering on behalf of all. Anis also. Good. Okay, so let us start again. We will basically pick up from where we left. That is, we were talking about anisotropic media. And remember that this is basically some. So if I again go back to what we had started out with, saying that okay, let me share my screen. Yeah, can you see my screen?
Yes, sir.
Yeah. So basically, this was the sort of picture that I had given you, in the sense of this is the big picture of what we are trying to do here, in the sense that this is actually the setup that is required. This is the setup for trapping microparticle and nanoparticle immersed in a fluid using light. And what we have is some kind of, this is the light that is used for trapping, and we kind of direct. So the light is polarized. This is a half wave plate by which we can change the polarization, and then we route it through these optics, this and this, and then this is again something which is called a polarization beam splitter cube, which depending on the input polarization, the transmitted light, it will transmit light which has p polarization and reflect light that has s polarization. So you can actually, by a combination of this and that, you can actually change the intensity or the power of the light that is incident. Okay, and then we have these two mirrors, and then this is a mirror, and this is of course not an ordinary mirror. Both D1 and D2, these are dichroic mirrors, which actually have differential reflection and transmission depending on the wavelength of light incident. So then we have this very powerful, sort of very short focal length lens, which focuses the input beam into this very tiny focal spot here, which is diffraction limited, in the sense that the spot size is close to the wavelength of light, and that the particle that finally you sort of this in the focal spot, you can actually confine a particle optically. That is called optical trapping. So what we have covered till now is how these lenses and all these work, and at present, I mean, depending on with the material, this may be like, if it's a dielectric, then in so okay, I am not probably correct in saying that we have gone to we've studied how lenses work, because that is actually the topic of our next only one of the topics that we'll be picking up next week. So how lenses focus light and all that we have not done, but how light behaves when it comes into contact with the dielectric material, that is what we have done. And we have also seen that how these reflect and transmit, and what happens if you have metal coatings on mirrors, optics of metals, as we did. And at present, what we are doing is how polarization is affected by optical materials, and these are a special class of materials called anisotropic materials, where depending on the incident polarization, which is also, that means the direction with respect to the optic axis of a certain crystal. So optic axis is that axis where you will have the same refractive index irrespective of input polarization, okay, which is the refractive index of the material. But these are essentially materials where the refractive index depends on the incident angle, that is how light is incident upon the crystal, at what orientation light is incident upon the crystal, that will basically uh, decide what kind of refractive index it's going to face. And we are now studying that in detail. So what we had covered there, what we had seen there, very, very interestingly, is that the whole story becomes quite a bit different. This is sort of, I think, a representative picture here, where we saw that, yeah, so this is a very nice picture, which tells us, which showed us that you do not, so the interesting thing here is, instead of, so D and E are no longer parallel to each other, because the crystal is anisotropic. So the properties, or the crystal properties, are direction dependent. So what we found was that D is the the field that is inside the material, which is basically caused by the polarizability of the material and all that. So that is the one that essentially we typically consider when we try to define polarization and all. That is perpendicular to the direction of propagation, not E. And we also saw very, very crucially that the pointing vector is also not in the direction of the propagation of the wave. And indeed, there is an angle between the direction of propagation of energy and the pointing vector. Okay, so very crucial is that this is this so now different kind of materials have different symmetries, and depending on that symmetry, you actually have different refractive indices that a wave encounters when it is incident on that particular medium. So today we will basically look at that. We will try to understand what these different type of materials are. What we also learned very importantly is that when you have a certain random polarization incident, if the direction is along one of the principal axes. Okay, so what we actually saw, very another very important thing, is that the total energy actually is, you can actually make these surfaces of constant energy, and that can be represented in the form of a sort of constant surface, which looks like an ellipse. Let me just dig that out from the notes. I think that was maybe somewhere here. Yeah, this one. Yep. Yeah. So this is the kind of surface that we had. This is a very crucial understanding that we had here. Yeah. So what we saw here was that, as I wrote here, in all three directions there exist a pair of solutions, n1 and n2, and these are solutions for n. Okay, and these are three principal Ri, principal the refractive index along the principal uh, axes, as we call them. And if an incident wave comes in the direction of the principal axis, then it's so in that case the electric field is basically parallel to the dielectric the displacement field. And so it basically encounters, the refractive index that it encounters is of course given by nx or ny or nz. But for any arbitrary polarization, what we saw was you can actually have two possible d's that are allowed, right? And each of those will actually propagate with different refractive indices, which is the basic root of any linearly polarized light. picking up circular polarization, because what happens there is that when you are not along the principal axis or optic axis, along sorry, so optic axis is basically that axis or that direction along which the refractive index is independent of polarization, as I said. However, if you are at an angle with respect to the optic axis, then what you have is that the incident polarization splits up into two different polarizations which actually travel at different velocities, so that when you come with linear polarized light and when you are incident on uniaxial crystal in order to get circular polarized light, what happens at 45 degrees, you actually have the incident polarization split into two different polarizations. Again, they of course they travel at different velocities, and when the wave comes out, you again mix them, so they are sort of recombine. And once they recombine, the effect of the phase lag of one of the polarization components result in a rotation, essentially a phase or in the total electric field, so that now you actually also you actually have light which is the ex and ey are at 90 degrees, and the resultant electric field is like it inscribes a circle with respect to the direction of propagation. That's called circularly polarized, right? Okay, so if we continue in that vein, we will basically now we will sort of define what we probably hinted last time, and that is something called the index ellipsoid or the indicatrix. And this actually is so this concept essentially comes from that equation that we wrote for constant energy. Okay, we defined that constant energy surface when we were actually writing down the wave equation and all that. So from del dot d equal to 0, we wrote down some, some condition on this, kx, with k's and n's and all. So in that similar vein, what we can kind of write down. So we saw that we got an ellipse, an ellipsoid equation of a surface. So the surface basically described an ellipsoid. So now so remember that equation essentially was kx square by n square minus nx square, and then again in y and z, similar things. But what we can now write in the same vein is we kind of define this ellipsoid or an indicatrix. So basically we write down a surface which is given in this form. This kind of a form where we uh so so this is basically similar to the constant energy surface that we had defined earlier, albeit there is a scale factor. So this is essentially, uh, this is not exactly what we wrote before, but so this is equivalent, one can say, equivalent with a scale factor, scale factor to the surface mapped out by the d vectors, giving a constant energy density at a certain frequency. Okay, so this is basically called the index ellipsoid. So see, just understand the picture. What we are saying is, we got that relationship with those kx square and all that sort of thing. In the same vein, in that manner, what we are saying is we are mapping out some kind of a surface which has only the principal refractive indices now, and we shall try to understand any material, we shall try to sort of describe any material in the sense as to how the symmetry axis of the materials is with respect to the principal refractive axis, principal axes, which are described by this which is described basically by this ellipsoid. And if you essentially have, the symmetry axis coinciding with one of the principal refractive axes, sorry, the one of the principal axes which have the different refractive indices indices, then you essentially do not have any, differential sort of refractive index depending on the polarization. Okay, so when you have like large, so for example with cubic symmetry and all, so all the three symmetry axes, they are essentially parallel to the nx ny nz axes. Okay, so that is very crucial. So of course the least symmetric crystals are the triclinic ones, where the axes of the crystals are have any random orientation with the refract with the with the principal axis. So those are the most complicated materials, anisotropic materials, and they're in sort of making devices and all. Those are least used because they are very difficult to control, in the sense that you have arbitrary refractive index. So if you just change the, rotate the crystal with respect to incident light that is coming in, you have very, very varying properties. Okay, so typically those are not used so widely for kind of making any sort of uh, any useful sort of optical devices, you can say. Okay, so what you basically have, so let us again maybe just describe this a little more quantitatively, so or rather just write down the pan. So basically these principal axes, these are oriented inside the crystal, rather a crystal I should say, inside a crystal consistent with the symmetry axes of the crystal. And so what basically, again let me just write down this. So basically for crystals with like perpendicular symmetry axes such as the cubic and tetragonal or hexagonal or trigonal, orthorhombic, all these orthorhombic orthorhombic. So essentially, your nx, y, z are parallel to the symmetry axes, right? And so by the way, so this is, as I said, this is the indicatrix or the index ellipsoid as we call it. uh, but for other things, what you have, for example, if you have more complicated crystals, like say monoclinic crystals, right? So monoclinic crystals, acha, by the way, have you guys done all of these different types of crystals and all? Do you have any idea of what monoclinic is and what orthorhombic and all these things in any solid state course? Huh?
Yeah, I think
Yes,
we
yes,
have
yes, we
done
have
in the
done the
beginning
Bravo
part of
analysis.
our CMP course, condensed matter.
Basically, for example, monoclinic, right? So monoclinic, you have these ABC, na? So
ABC and alpha, beta, gamma.
yeah, alpha, exactly. So basically, you have this B axis. So for example, more crystals with lower symmetry, such as monoclinic, or triclinic, are much more complicated, are more complicated. So for example, in monoclinic, we basically have this B axis, which is perpendicular to your A and C, but uh, A and C, the B is perpendicular to A and C, but these A and C are basically at acute and obtuse angles with respect to each other, right? A and C, which themselves are at sort of acute and obtuse angles, right? So basically, what you have. So, for example, let me try to draw one. Let's try to draw one. So you will right. So this is a bit complicated. Let me see if I can find one. It's better to put a thing than just drawing. No, let me see if I find one. It's much easier to monoclinic, just take from the paste from the thing, right? Because my drawings are, I think, much better things one can manage with monoclinic crystals. Where are they? Oh, yeah, found. Okay, right. Copy image. See, this is one of the advantages of online. No, it's far better in order to just go and use the internet resources than classroom teaching, I guess. Okay, okay. Just to control V. Oops, this is black, is it? Oh God. Oh, horrible. Wait, let me just try to save this thing. Why is this like this? Oh, but okay. Oh, damn. Mm, what, man? See, this is the problems of. Achha, if you just okay, maybe I can take a screenshot. No, that is easier. Yeah, it will be easier. Yep.
And you can crop it also, I think.
Yeah, I think I can crop. Oh shit! Wait. Where do I crop? How do I crop? Is there any way of cropping here? Oh, damn.
Sir, the scissor thing I think was the
So is
crop.
the thing I just completely deleted, no? That is cut. That's not crop.
Oh,
Wait, let me just crop in PowerPoint and get it back. It'll take 2 seconds. This is irritating. Anyway, so it's very clear that you have basically just yeah. Let me just finish this.
Sir, even this is fine. Like we can
It's
get the
fine.
idea.
Yeah, no, finally when you use a note, it's better to have it properly. I keep this takes 1 minute, not even that. Just takes less than a minute. Yeah, done. Finished. Yeah, so beautiful. So basically, this is what I'm talking about. So you have your this one A, this is perpendicular to both your B is perpendicular to both A and C, but these individually these are at different angles. You have alpha, beta, and all that. So now, what is very crucial? So what is the takeaway from this? The takeaway basically is in this uh, case, the indicatrix is what do you think what will happen to the indicatrix? So yeah, so you have this B is kind of a symmetry axis which is perpendicular to both A and C. These are A and C are basically having any kind of orientation. So what do you think will happen here for a monoclinic crystal? Yeah, what do you think? So you have one, so basically, yeah, what is the general understanding? Yeah, what? See, I mean, just so what we said was if you have these symmetry axes which are cubic and all, then the indicatrix basically has all the axes parallel to the uh, internal symmetry axis. So here, what will you have then? What? Huh? So it will have only one axis, right? So only one of the axes will be sort of in the direction of this B. The others will have completely random orientation. So these A and C will be completely randomly oriented with the indicatrix. But this one of them you can always take parallel to the nx to one of the things, right? So basically, indicatrix will have one axis which is parallel to B, while the others will have any orientation with respect to the principal axis.
So why not A?
So typically that is the one which is so B is the one where A and C, which respect to which A and C are perpendicular to, na. So that has like higher symmetry. That direction has more symmetry than the other ones. So typically that is the one that we consider as one, because A is again A and C have random angles, whereas B has the same angle with both A and C, right? So when you have so when you so think of this, we are trying to understand the isotrope or an anisotropy or the isotropy, whatever you say, of the crystal with respect to its properties. Okay, so we are trying. This is again very much like a projection of
Oh,
my
okay.
symmetry with respect to my principal axis. Okay, so one of them I'm taking along the B because that is the one which has highest symmetry inside the crystal. The other
Oh,
one will have some kind of a dot product, right?
yes, sir.
Is it clear? You understand, right? So that is very
Yes.
fine, very nice, right? So this is absolutely like what we have in quantum mechanics, but this triclinic is essentially all three axes. This is the most complicated one. Have random orientation with respect to principal axis. Now the question that obviously should come into your mind is how do we determine, like, if there is a random vector which is basically incident, then what is the way of determining the refractive index that the wave vector will actually perceive? That is very crucial. That cannot be completely random, right? It cannot be that it is like there is, I mean, there have to be some sort of boundary conditions or some kind of rules that it has to obey. It's some sort of set, you could say some kind of set algorithm, or some manner in which one can predict what the wave vector, or I mean what a randomly polarized wave will encounter when you essentially come in with 1 minute. Let me when you sort of come in with a very, so a random polarization with respect to the uh, principal axis. Okay, so for that there is something known as the intersection ellipse. So what is that? Let me just again use our nice way of cutting and pasting. Okay, so let me just write this down first. The concept of the intersection ellipse. So essentially, this is nothing but the projection of the symmetry axis with the your this thing. Uh, क्या बोलते हैं? In I mean the indicatrix. Okay, in the sense, or rather, it's better to say that it is some kind of, the wave vector, the k vector has some direction, right? And perpendicular to that we define a projection, we define the polarization. So how does that sort of, that polarization, it intersects? If I now draw, so let me just directly draw that. So it is something like this. Okay, so basically what you have is, this is your k vector coming. Okay, and this is your that indicatrix, that surface that we defined by the refractive indices. Okay, so basically, if you, so now we have a certain wavefront, right? So that wavefront is going to intersect with the indicatrix. That surface also gives, because this is an ellipse, and of course you are assuming some kind of plane wavefront here, then that also will give you some kind of an ellipse. This is called the intersection ellipse. And these two axes, that the semi major and the semi minor axes of this intersection ellipse, basically give you the d1 and d2. These are the direction of polarizations, and the length of these basically are nothing but the refractive indices. Okay, so this is very important as a concept. So you're coming k vector as a certain direction, so there's a wavefront. Now I just see the projection of that wavefront on my ellipsoid, my index ellipsoid. And whatever I have, so you remember that we saw that there are two orthogonal directions of polarization that are allowed, right? So those are d1 and d2. That is very crucial, right? That is very fine, and we saw that they were perpendicular to each other. That also we saw. So just extending that, we can say that this is going to be unique. And why is that unique? Very important, because you cannot have the stored energy dependent on the polarization direction. I mean, the energy cannot change if I if I change the orientation of the crystal with respect to the wave, I cannot change the amount of energy that is sort of generated, right? That will sort of violate the second law of thermodynamics. That cannot happen. So that has to be constant for a given refractive index crystal, for a given input polarization. That has to be the same. So then that you can well understand that if I have come with some, some kind of a k vector, some direction, and I rotate the crystal arbitrarily, basically these will change in such a way that the total energy always will be constant. The energy that is, stored in the crystal, that is dissipated by the wave inside the crystal, that will always be the same. And how is that the same? Because these d1 and d2, so and very crucially, this d1 and d2 have to simultaneously satisfy, this they have to be perpendicular, they have to be part of this ellipse, and they have to satisfy the Maxwell's equations at every possible, both of them have to simultaneously satisfy the Maxwell's equations with the appropriate n1s and n2s that will basically evolve, or that will be derived as a result of this d1 and d2. Okay, they have to simultaneously form this, be the semi-major and semi-minor axes of the ellipse, and they have to also describe the Maxwell equation. Very crucial. So let me just jot this down. Okay, so basically what I'm saying is, if the wave vector is along a particular direction, then the wave front, so that is basically k, this is essentially k, the wave front that is perpendicular to k intersects the indicatrix along an intersection ellipse. Okay, ellipse. And so what you have is the semi-major and semi-minor axes give the directions of d1 and d2, and the axis lengths give n1 and n2. Very crucial. Okay, and essentially the reason that is very crucial, that this has to be the way that we are describing, is that so we just say that the reasons why this is imperative is that the stored energy has to be has to be has to be independent of the polarization direction. Otherwise rotating the crystal will result in would result in absorption or even extraction of energy. which is absolutely impossible, right? So this is very important, and there is another point which I again let us write down. That is basically that this how it is determined. Let us just write that down, and
So
that
I
is
have a question.
yeah. Just one second, Hitesh. Let me just write it down.
Yeah, sure.
So only two perpendicular directions of D1 and D2 satisfying the conditions of acting as major and minor axes of the ellipse with the corresponding n1 and n2 satisfying the Maxwell's equations. N1 and n2 satisfying the Maxwell equations. Yeah, tell me.
Yes, sir.
Yeah.
So
Hmm.
D1 and D2 has to be orthogonal. That part is fine.
Mm-hmm.
But how do we came to the conclusion that they have to like D1 and D2 have to be along semi-major and semi-minor axis?
No,
Because
so
as you
conclusion
said
nahi.
that
So
this
we
has
are
to be independent
basically
of polarization direction.
the what was the last part?
The thing is, this because the energy stored has to be independent of polarization direction. So
Hmm.
this direction of D1, D2 cannot be uniquely determined, isn't it? That
No, why not? In the sense that, see, I have to basically satisfy a lot of stuff, right? So you have to ensure that the Maxwell equations are being satisfied, along with the fact that so the D1 and D2 are mutually perpendicular. You can say that whatever the orientation of this intersection ellipse is basically gives the properties of the I mean the no so it just tells you what kind of refractive indices the particular wave is going to encounter, in the sense that don't look at it that way. It is the other way, in the sense that you are trying to find out what environment, or can you quantify the environment which the incident wave is going to environment that it is going to face inside the crystal. Okay, so that we are saying. But this was sort of expected itself, right? We said that there is going to be two allowed directions of polarizations, we said, right?
that is
No,
fine. But how do we
yeah.
you uniquely say that they has to be along
No,
semi-major and
no,
semi-major
in the
axis?
sense that I am saying that how would you sort of define the, so you have the indicatrix already present, right? So that is how the refractive index I am sort of quantifying. I'm saying that the refractive index I'm sort of drawing as a surface. Okay, and that surface, I take the projection of that surface, or of my wave vector on that surface. Basically, that's what I'm doing. That I'm taking the projection of the wave vector on the surface. And so see, D1 and D2 are the directions. Remember that. And the projection means that it is orthogonal to K, right?
That is fine. But they
So
can
then they
be
will form an
orthogonal
ellipse also,
in
right? Now think
even
of
in
this.
uh,
So D1 and D2 are the directions. The lengths are the refractive indices.
that is fine.
D1,
I'm
D2 are
just
not
talking
the.
about the direction. I mean, they can be
Uh,
orthogonal, but the
yeah.
direction need not to be along semi-major and semi-minor axis. That's all I'm
No, but
saying.
then. No, but then in the sense that. No, but direction is. Uh, in the sense that see, I mean, when you have the projection that you take on the in intersection, I mean on the indicatrix, that will be an ellipse. Okay, and now I'm saying that this is so there are two directions of polarization that we said are possible. Okay, so we also want to see what kind of refractive index the wave will encounter. So in order to quantify that refractive index, that is where I'm saying the length is what is crucial. Okay, the length of the this one and this one. So that is basically how you describe this ellipse, na? I mean,
So
semi
like
major and semi minor are what
okay,
are how you describe the ellipse.
initially what I thought is like the statement that you have written
Hmm.
at the top. It says that this intersection ellipse is basically the
Hmm.
intersection of the indicatrix
Wavefront.
and the wavefront.
Yes, yes,
So this
yes.
gives you
So
this
that gives the yes,
intersection.
right, right,
So
right, right.
then from here, how are we concluding that the D1 has to be along semi-minor and semi-major axis? That part I just didn't get.
I mean, see, how we are. So
When you say that this is the case, then you're saying that the direction has to be unique.
no, in the sense that direction, yeah, of course, the k vector is unique, right?
The
The
K,
k
that's
vector is
fine.
of
I'm
course
talking
unique.
about D1 and D2. You're saying they has to be
Ah,
unique.
yeah. So basically, no, but the directions of D1 and D2 are okay. So now, why they are in the no? See, that what we can try to think of is remember. Okay, yeah. So I think how we can defend this is that you remember the equation that we wrote, na? So that was basically some kind of D by n squared minus nx squared plus that thing, right? So that will be so there is if I remember that equation we had 1 minute, so that basically had a kx square. So basically that was a yeah, so we had a the the numerator we had in the constant energy surface, that was basically some kind of the dy dx dz that were defined by some kx px square, right? If you think of it, just if you look back at the notes, we had del dot d equal to 0, na? So from that we created this surface, right? We created this constant energy surface. So remember that my index ellipsoid is actually similar to exactly the same thing with a scale factor. Okay, so
I'm
that
not
has to be
questioning that
satisfied,
why it
right?
has to be ellipse.
No, so
I'm not.
that has to be satisfied. So I'm
Yes, that is
saying
fine.
if that has to be satisfied, what is seen is that simultaneously satisfying that, which is basically satisfying the Maxwell equations, and also ensuring that the polarization is independent. I mean, sorry, the energy stored or energy interaction, energy sort of exchange with the crystal is independent of the polarization, gives you solutions where my D1 and D2 are semi major and semi minor axes of the ellipse.
Oh, okay, so like maybe I have to work out the
Yeah, so
solution because
basically
I
what they are,
didn't get this as easily. And
yeah,
this
in the no, but see that I mean, whether, see, what I can see is that you have these as the original equation that we had when we said d dot del dot d equal to 0 was that you have kx squared by the cx squared minus c squared and all that, where your kx your d, it's essentially dx kx dx plus ky dy plus kz dz equal to 0. Okay, so basically those your d1 and d2, if you saw, they are sort of given by my projections on the principal axis, right? My d1 d2 were projections on the, see, remember my d, if you again saw the notes earlier, the dj1 dj2 are like kj and all that, which are basically projections. So now you think of it, I am actually getting an intersection ellipse, and they are describing. So basically, if they are describing an ellipse, then the principal axis essentially is the refractive indices, right? Mane, when you write that kx square by by I mean x squared by nx squared plus y squared by ny square, I'm saying that the semi major and semi minor are basically these things, right? I mean,
so
right? So then the D's are in that direction, right? So whichever direction these are, right? My index ellipsoid is, the projection to the index ellipsoid is. So essentially, you can say that it has to be perpendicular to the k vector, and which is cutting this surface. Okay, now whether we can, I don't know whether mathematically whether we have any definitive proof. I don't think there is. Basically, what we understand. I mean, see again. I think if you really sincerely ask me, I think these are recipes. Okay, these are recipes to understand these things. Okay, whether there is any concrete mathematical, I think again, I think we are, as I said, we have to kind of have the Maxwell's equations being satisfied, and of course they also have to fall on that ellipse. This is very crucial. I mean, I have one sort of intersection ellipse, and I know that I have kx dx plus ky, that is 0. So simultaneously both conditions have to be satisfied. And
Yeah, I
then
mean, isn't
whichever
this
ellipse
question
has
gives us
these as
that
the
they have,
principal axis, that is your ellipse. Okay. So
yeah,
what I'm claiming is whichever ellipse has these as the major and minor axis, that will satisfy both conditions. Okay. This is what we are trying to say.
like maybe you're saying that we are defining them this way.
Kind of. But also no, but at the same time, I'm also saying that I need these D1 and D2 to fall on an ellipse. I mean, because obviously these
Yeah,
are
that is fine.
falling on
That
an
is
ellipse. Huh. But I also need them to satisfy the Maxwell equations. So when I do that, I basically say that, and it's
so
like also
that
convenience
gives
that
you
way.
the condition that they have to be orthogonal.
Yeah. Orthogonal. Okay, you're saying that why am I not choosing any random pair
Yes,
to be uh,
any orthogonal
that
pair that lies on the intersection ellipse.
any orthogonal. That so see one thing that you can think of if you go the other way. See, when you have a crystal which has cubic symmetry or something, then this ellipse becomes a circle. Okay, and in that case, it is does not make any sense. All the directions are the same, right? Because it's now a circle. Okay, so in there, you so that has higher symmetry, so it does not matter which direction these are. Okay, it's only when you reduce the symmetry, then we go from this this condition where any direction of d1 and d2 is fine, to the requirement that you need to have these as the major and minor axis. In the sense, I would say that it is more important in terms of the refractive index, because the refractive index values that you choose are those along the so yeah, so that is the so intersection ellipse that you have. Basically the length of the major and minor axis give you the refractive indices, because remember that cannot be arbitrary. Okay, the refractive index cannot be that has to be the same, that has to be the same for an incident k direction. It has to be in the sense, depending on the k direction it will change, but you cannot have that for the same k you have different possibilities of n1 and n2, right? The only unique things that you can have are the major and minor axis, which are unique. You understand my argument? I'm saying that if you take any pair of d1 and d2 which are perpendicular, then the constraint will come, that the issue will come that the refractive indexes, the refractive indices will also be, because that will then the length of that will be the refractive index. The length of that arm that you're taking, or that projection that you're taking, that will basically be the. So then for the same kind of k vector, you have all possible pairs of refractive indices. That cannot happen. So I'm saying uniquely you have to simultaneously solve the thing that they have to be on an ellipse, they have to satisfy Maxwell's equations, and they have to give a unique pair of n1 and n
Sir,
for the
but
same k vector.
we can define like that the D1 and D2 will be defined at say at an angle theta with the major and minor axis. In that case, it doesn't become random anymore. It again becomes unique.
No, but then you can choose the theta arbitrarily, right?
Yeah,
I
but
can
but,
keep on
but
choosing the theta arbitrarily. Then what is my refractive index?
yeah. So
If I keep on
basically,
choosing theta arbitrarily, then I do not have the same, I do not have the same refractive index for the same k.
Right, but what you are doing here is that you are forcing that theta has to be zero. But I can say that
Correct.
okay, theta has to be 30 degrees. Then even then it's unique, na. In that sense, I am saying.
No, it
Yeah,
has
see,
to be parallel.
it has to be
Otherwise,
parallel.
that Fresnel equation will not be satisfied for refractive index. It
Yes,
has to be
basically,
parallel.
yeah, it has to
Okay.
be, but a parallel to this, yeah, but again, Vishwajit, if you think of a triclinic or something, that
No, no,
makes
no,
that has no parallel, right?
no, no. When you are drawing the ellipse, means that indicating ellipse,
Hmm.
that D1 and D2 has to be parallel, have to be parallel along that semi-axis. Otherwise,
Yeah,
that
yeah,
yeah.
yeah, yeah.
So
So no, that is, but then see, I think the condition, I think what they're trying to ask is that a natural condition? Is that something that we are defining to be?
Yes, sir, exactly.
Is that, are we defining that to be, or is this something? I believe it's something that will come if you actually have these simultaneously. All these have to be satisfied. When you have
yes,
the
means
final
you
equations satisfied, I
and
mean,
that
Maxwell equations is basically final equation.
yes. So both have to be satisfied only if this is parallel.
Yeah, 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 exactly, exactly. So that is what I'm saying. So if you work this out somewhere, then you will actually observe that. Okay. So now let me just define something like the optic axis. So that is basically, uh, so basically that is, yeah, so that, so yeah, so essentially that optic axis defines that direction of k where this intersection ellipse is the circle. Okay, very very clear. So basically it is nothing but the directions sorry, of k through the center of the indicatrix where the intersection ellipse is a circle, nothing but that. Okay, right? So that, so basically that means your principal optic axis is fixed for a certain crystal and for a certain frequency of light. So it is fixed for sorry, right, it is fixed for a certain crystal certain crystal for specific frequency of light, and very important, the Ri is independent of polarization, independent of polarization. And so basically fixed, it is fixed, and waves of fixed for waves of all polarization. So this is a very interesting definition of the optic axis. So this is clear, right? So basically that intersection with respect to the ellipsoid, that sort of where my I have a certain k vector where the intersection ellipse is no longer an ellipse but it's a circle, right? So this is very interesting. So for example, when you have crystals of like higher symmetry, so let us just go to describe some of these stuffs, and then we will just describe a little bit of the uniaxial crystals in detail before we by wind up this entire topic. So basically, if you think of cubic crystals, very clearly the indicatrix is always a sphere. is always a sphere and there is no specific optic axis. This is extremely important. Okay, and so therefore it is very clear that the wave propagation is independent of of k and d direction. So independent of what kind of intersection that you have with the angle with respect to the crystal, that does not make any difference at all. Okay, so but then some other for lower symmetry. So I think I should just make this symmetry considerations. This is the title of this. Okay, so then you also have things like trigonal, uh, then these are the tetragonal, hexagonal, and all kinds of stuff. So typically in those cases you have your nx equal to ny, and there basically the indicatrix is an ellipsoid, and the optic axis, there is one optic axis, is along the direction of highest symmetry. I think that is called the C axis or something, the C axis. So these are, this whole class of crystals are called your uniaxial crystals. Okay, very, very crucial. So these are the most commonly used materials for any birefringent medium. Okay, because these are very simply, these have these one direction along the optic axis where the refractive index is independent of polarization, and one that is different. One will dip down, that will depend on your incident angle with respect to the optic axis. So basically my equation of the indicatrix becomes sort of simplified to something like this, and I'm sure you know what NO and NE mean. These are nothing but the ordinary and the extraordinary axes. Okay, so I will, let us just again maybe just draw these, show you what these are. Yeah, I think these are fine. Just give me a second. So there are positive and there are negative uniaxial crystals. So when you have your Ne greater than No, it's called a positive uniaxial crystal, and when it's other, when it's vice versa, then it's called a negative uniaxial crystal. Right. So let me just draw. Just these are again from the textbook that I think I told you. Yeah. Yeah. Okay. Yeah. So let us just write this. So there is this optic axis that is NO, typically NO, and this is the NE. And in one case, the NE is more than NO. So essentially, you have so it's basically you have two possible polarizations that are parallel and perpendicular to the optic axis. This is called the E waves, and this is called the O waves. Ordinary, extraordinary. So polarization is perpendicular, right? So that means the direction will be opposite. So direction mane, so the direction, that is the k vector that is in the direction of the optic axis, that will lead to O waves, and the k vector that is perpendicular to the optic axis, k vector, which means that the polarization is parallel, that is leading to E waves, right? So very interesting. So NO is index that is perpendicular to optic axis, and NE is index parallel to optic axis, right? And you can say that, when NE is greater than NO, you have positive uniaxial crystals. Obviously that means that your VO is greater than VE, and when you have NE less than NO, you have negative uniaxial crystals, which means VO is less than VE. Okay. And also, these are quite obvious, like, things like, uh, your for O wave. So basically, so okay, so O, and let me write, this is ordinary and E is extraordinary. Okay. And these are, I think we have mostly covered. So we can basically say that for O wave, you have, dx is like epsilon O. Yeah, that is just epsilon ax, and dy is epsilon O epsilon ey, because again there is no this thing. And very clearly, your yeah, because it's a circle, so epsilon xx equal to epsilon yy, which means that d and e are parallel for your O wave, O ray or O wave, and uh, yeah, it's basically perpendicular, and the polarizations are obviously, that means perpendicular, whatever. But for E rays, this is not the case for E wave or E ray or whatever. At times, books call it as E ray, E wave. So, acha, so there is one thing that you guys should perceive. So, ray, when we say, that is typically in the direction of the pointing vector. Okay, so E ray, when we say, that is the energy direction. Okay, and the wave is typically the polarization direction. So typically for for optic axis, I mean, sorry, for homogeneous medium, for isotropic medium, for isotropic medium, the ray and wave, they are the same. Here it is not the same. Very crucial. Okay, ray is typically in the direction of the energy, right? So basically, what we say is, ray is that is the E ray is not parallel to the wave vector. Okay, so basically, yeah, so the pointing vector is let me just write, I think we just write this down. So yeah, ray direction S, and yeah, wave direction is K. So this is perpendicular to E, this is perpendicular to D. And obviously for any isotropic media, these are degenerate. So these are absolutely the same. Okay, ray direction S, let me say energy or ray direction. And this is polarization or wave. Okay, so this is basically what we will cover in your isotropic, sorry, in your yeah, an isotropic media. I will give an assignment maybe today, a couple of questions we can give. So yeah, so what is the, do you have a picture of this now? Yeah. Oh, by the way, so there are some biaxial crystals as well, so that probably we should say. So things like, So all those triclinic, monoclinic, those are called biaxial crystals. Okay, where you do not have. So let me just write that down. Yeah. So yeah, orthorhombic, triclinic, monoclinic. These are biaxial crystals, which basically I have, like, you do not cannot define an optic axis that way. Okay, so tell me guys, any questions? What is the general takeaway from here? And any sort of do you have a picture of this? Because that is what I'm really interested in. You guys have to have a picture. Yeah. Huh? What? Any thoughts? Anything that you feel that one can discuss on this, or is this fine? Huh? So okay, so have you guys started working on your this thing? What is that? Term paper? What? Nothing.
Sir, yes, sir. How
Uh,
long should the presentation and the paper
Half an hour.
take?
Half an hour.
Oh,
Half an hour to
okay.
40 minutes, not more than that.
Okay, sir.
No, paper. I'm not putting any limits. Paper you should try to finish in 4 pages, which is the PRL standard. Okay, four pages, double column like they have in PRL, or you can do single column. So if it's single column, then you can make it within, like, I will send you a recipe. I mean that tech file. So it has to be done in tech, by the way. So I think that is. I think physicists have to learn tech. I'll send you the thing. Uh, the maybe the, but then see, I don't need to send. Yeah, it is there in overleaf.
Yeah,
Just go.
it is there in the
Everybody has.
overlay.
Everyone has. So
Yeah.
overleaf is very standard. It's like it is take in the form of word. Okay, so it's very simple. Acha, tomorrow we will do this polarization algebra, Jones and Stokes and all. So this one I will not spend too much of time. Okay, but I think most of you know this quite a bit, and I will very quickly skim over this. So I don't know. Maybe what do you think? I mean, can you guys do some self? I mean, I think you have anyway done most of the stuff. Maybe acha, Muller matrices did you do actually in that other in that? Yeah. So how familiar are you with Muller matrices? Muller matrix?
Um, we didn't do that in the last course. I don't know
Okay, so
which
then
course you're referring.
that probably will take up that then. Okay, so you want that to be covered, no? So Muller matrix maybe I will spend some time. Okay, okay. So Muller matrix that maybe cannot, that one day is maybe a bit tough. Let
Sir,
me see.
like those who have done the spatial light modulator experiment in the
You
physics
guys
lab.
did, no?
Yes, sir. Like I don't know in this course how many have done that, but whoever done that
Mm.
must know about Stokes
Yeah,
Muller.
yeah. Stokes Muller algebra you guys had all done, no? Acha, uska
Yes,
actually manual is very good, no? I think Dinwalo wrote that manual. I think that manual was quite educative, right? By the
yes,
way,
sir. Like
Hitesh,
sir
do you
even
have that
delivered a
manual?
lecture.
Can you send me the? There's a theory part of that manual, no?
Yes, sir.
Okay, let me see if I don't have it. Can you? I don't remember. Can you just mail me that manual because I might not have it. I
Sure,
don't
sir.
remember if I have it. Huh? You guys have it, right? Yeah.
Yes, yes, sir.
Huh. So can you just send me then? I don't think I have the manual. I don't think I have the manual. No, I might have, but I'd have to search. Can you just send me that Stokes Muller manual? I mean, the theory part, not the experiment. Experiment is not needed. There is a theory part, right? Huh?
Yes, sir.
Yeah. So can you just send me that manual? I think that was a very well written manual.
Yeah,
Okay,
sure.
ठीक है. Okay, so tomorrow we will meet then. 5 o'clock. Yeah, and I will try. Let me see if I can send some assignments then by tomorrow. Okay. Oh God, this is going to be saved in Himang's